first question asks you to draw the structure of a 2 degree of freedom feedback controller and show the different signals including whatever. And therefore, what is this all about? And explain their physical meaning. Structure of the 2 degree of freedom. How does this be 2 degree? How does this what we're drawing is as 2 degree? The plant itself is itself. Alright, it has its own transfer function. We call this P of S. Alright, you cannot change your plant system, you cannot change your plant transfer function. And therefore, normally we want a controller C of S, which is a certain transfer function that will control your plant. And this controller is the first degree of freedom. Okay? If your filter now is also a transfer function, or some constant in the other hand, I think it should be a transfer function, then instead of just the controller controlling your plant, you require a filter to also control your plant. So if your controller is not good enough, you can use your filter to improvise your controller's performance such that you can make a good plant out of it. So therefore, this is a second degree of freedom for your system. So therefore, if you have other feedback, maybe K of S now, alright, then you're going to talk about a third order of freedom, alright, trying to control your plant also. So these are the things that you may need to know. Alright, and you need to label this one is your so-called your reference signal. Alright, you should write as reference signal, tell them that it's reference signal, or you call this the command reference signal or whatsoever. This is your error signal, this is your input signal into your plant. Alright, and this is the disturbance, that what they want is to include the disturbance, and this is the noises. Alright, and this is your command response, Y. Alright, we call this the output. Alright, so to speak, this is actually your control signal. I should say that this is called the control signal. Alright, not the input. Alright, the control signal, you should define it properly. And then this is the negative sign, because it's feedbacking now. Alright, and therefore these are the little things that you may need to consider. Alright, ask you to compare your contrast the properties of an open and a closed loop control structure in relevance to the plant disturbances, changes in the gain, and stabilization. Alright, therefore the first thing, if you're going to talk about, let's talk about the open loop system first. Alright, if you have open loop systems, for example, input your reference signal or your command reference signal, you input into your plant, and then you have a certain output or your output command response. Alright, you may have a certain disturbance halfway, we call it D of S, or maybe N of S halfway also. Alright, so therefore if you open loop, your input goes in the plant and being changed by, so the plant actually moves, but the disturbance actually changes your plant's position. And perhaps if you have a car over here, for example, and then you input a certain controller signaling it that okay, you go. However, you want to move it to this point over here, but along your way, when you move here, alright, there may be a disturbance that push your car. Then your car will actually move to the other side. And because there is no feedback signal telling you that you have been disturbed, then you will continue move over here. But however, you are not at your desired output already, because your desired output is this position, but we will stop at this position. Ta-da! And therefore this is not good, and therefore provides no compensation for disturbances. Alright, but I actually want to stress that just now when I draw the plant and the disturbance, I draw a noise, right? Don't take it that I have a noise over here. Alright, because a noise is simply for the feedback system, then you have a noise. As you can see, the noise is input to your feedback system. So normally for open loop system, only dealing with the disturbances only. Alright, if the open loop system does not provide any compensation for disturbances because you didn't compensate, that if your disturbance push you, you will want some feedback to tell you that disturbance has come, so you need to remove the disturbance and continue to go back to wherever you want. Alright, secondly, system is highly sensitive to the changes in the plant and the operating conditions. Alright, what does this mean? Actually simply copying what they write, but I just want to explain so that in the future when you revise it's easier to understand the meaning. So for the first one is that it's highly sensitive to the changes in the plant, is because if you were to input a certain signal to the plant, if the plant changes certain stuff, your output is going to give out a certain other stuff. if you input 1, even if you want your plant after your output is 1, however after your plant cock out, and then it multiply your responses. I mean you multiply your input and becomes 2, and therefore it's very sensitive to the changes of your plant. So the plant itself is very unstable, and you're gonna kill yourself. Alright, these are the things like that. And it's also sensitive to the operating conditions, meaning the disturbances that we talked about just now. Alright, the operating conditions meaning the disturbance, meaning along the way, even if your plant is alright, maybe other path the disturbance may cause you to be not cool. Anyway, last point. So the last one is building on the second one, which means that if the plant is unstable, you can't stabilize your plant. Meaning that normally if you have a plant over here, if this is unstable, which let's say you input 1 and then you want it to be 1, but however the plant itself output 2, so it is unstable, right? So therefore, without feedback system, with a controller to control your plant such that the plant still can work, alright, the plant, because of an open loop system, when your plant spoil means spoil, then you're gonna change, you're gonna waste money, things like that. So you can't stabilize your plant, and therefore a feedback system is good when you have a controller to stabilize your plant, such that you can alter your signal such that it becomes 1, things like that. Alright, and therefore the last point is that if the plant is unstable, you can't stabilize your plant, things like that. As for closed loop now, alright, for the disturbance, the closed loop has compensation for the disturbance. If you still remember, we have the equation for our this block diagram over here, right? We actually create an equation, right? This whole chunk over here, alright? And if you take a look, you have a system like this, 1/1 plus Cp ds. And we know that this Cp over 1 plus Cp is, we call this the T, right? The complementary sensitivity function. And 1/1 plus Cp is actually the sensitivity function. And we also know that T plus S is equals to 1, if you still remember. So if my S, you were to decrease all the way, alright, you make it very small, acceptably small such that your plant doesn't spoil, and your T is very high, such that your plant will not spoil also. Alright, this means that you're gonna attenuate your disturbance, or meaning you're gonna make your disturbance very small. And therefore, this is one way of doing your thing. You have compensation for disturbance already. Alright? Therefore, you can somewhat say that with minimizing of the sensitivity function, alright, we can reduce the disturbance. Or the magnitude, you were to say, because it's just 1/1 plus Cp ds. Alright, if you were to reduce this magnitude of this, you can minimize your disturbance. Alright, that's just what I want to say. Alright, damn it. And also the next one is system errors are less sensitive to the changes in the plant, alright, and the operating conditions. So it's just terbalik only, it's just opposite. Just now is highly sensitive, now is less sensitive. So you just simply write that, and then you can explain stating that the steady state error is less sensitive by a factor of 1 plus Cp steady state. I don't know what it means. Alright, 1 plus Cp is simply the distance from -1 to your Nyquist plot. Alright, this is 1 plus Cp. So a factor of this, I don't know what the hell is going on. You can just write that the overall system is less sensitive to changes in plant, contrary to the highly sensitive for the open loop. Alright, and the steady state error is reduced by a factor of this thing. Alright, I leave you to think about it in the future. So for this, if the plant is unstable, you can't stabilize your plant. For our case, you can stabilize your plant. Alright, but how do you stabilize your plant? We can do this by loop shaping, or using the controller to change your transfer function. In the last video, we talked about the proper and the improper system, right? And therefore, if you have a certain -1 over here, if your loop is very near to your if your Nyquist plot is very near to -1, then you can loop shape. You can change your controller a little bit and alter it, and eventually it will go to here now. Alright, somewhat safer, in a safer zone. And in order to measure, we measure using the vector margin. Alright, the 1 plus Cp, or S minus 1 in this case. Or you can also calculate by the phase margin, the angle from the -1 circle, or the gain margin, alright, 1 over lambda, things like that. Okay, so these are the tools for the closed loop system for you to actually find in terms of the stabilization of your system. And therefore we compared the open loop disturbances, the gain itself, and the stabilization. When you design a closed loop system, you want your output to be the same as your input. Alright, so therefore it's a stable command response, or a good command response if you were to design your stuff. Alright, but before having a good command response, you want to also design your closed loop system to be stable. Alright, and therefore when you design a closed loop system to be stable, you're going to loop shape. Alright, just as we say just now, you're going to loop shape and things like that. Stable for closed loop. Wait, by loop shaping, or you can check your vector margin, you can check all your stuff, phase margin, gain margin, and alter your controller. Choose a PID controller and things like that, so for stability. And then you will have somewhat of a good command response. And you can also need to also design a goal such that you can reduce your disturbances, or normally they call this the attenuation of your disturbances. Alright, so you want to reduce your disturbances such that, because t plus s is equals to 1, but because your t, never mind, let's continue first. Later on you will discuss the limitation, the next step now. And also we want a good robustness performance. Alright, and we want, the purpose of the good robustness performance is to ensure that when you perform, alright, you're robust against disturbance, you're robust against noises and things like that. So you have to design a system that is robust against any troubles out there. You don't want when you turn your fan, like you're flying an aeroplane, you spin this turbine fan, such that when a giraffe, what giraffe? Such that when a bird fly in, or maybe a sand fly in, alright, you're gonna somewhat change and stop the fan. Maybe the fan may be broken or whatever. Alright, when you spin, and then if the bird fly past, and then it's stuck somewhere, and then your whole fan is gonna die, and then crash and everything. So you have to be robust against disturbances all around, and therefore this is very important. Alright, let's relate to the limitation now. Alright, describe the factors which limit the extent to which your goals can be achieved. Alright, the limitation, the first thing is your plant capacity, because your plant cannot fully operate when T is full. Alright, if you remember your Cp over 1 plus Cp, and then 1 over P naught, this is your what do we call the control sensitivity function. You still remember, you can determine your T naught in this case. Alright, it's not the case, this is not T naught, but rather than this is actually C over 1 plus Cp. This is your control sensitivity function. So your plant itself, alright, is related to your T. I forget how is it related, but for such of the case that happens, alright, your plant capacity may not tahan such of a high load. So therefore you want your plant to be maybe operating about 0.8. If the capacity is kept at 0.8, you cannot exceed. If your system goes to 0.9, your plant is going to fail. So the plant capacity means the plant capability to deal with problems when it closed loop or things like that. Alright, I forget, you should go back and watch your plant capacity video and things like that. Alright, so the next thing and therefore this will also cause relation to your disturbance, because if your plant capacity is 0.5 or anything larger than that is unstable, then you're gonna have a S of 0.5 also, which is this S is multiplied for ds if you still remember, right? So if this increases, you're going to amplify your disturbance, and therefore you're going to also cause your disturbance. And therefore your plant capacity is a very powerful thing that will affect your disturbance and also your command response and the stability of the system. Alright, and also affecting your good robustness performance. So your plant capacity is a very, 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 very important thing you need to design. So therefore you need to choose the good plant in order to to design what you want, right? And let's say if you want your capacity, if your plant capacity is like T, alright, if it's like for example 0.8, if you still remember that particular equation, where is it? Okay, never mind, I just write it down now. Equation where T is your Cp over 1 plus Cp, and then S is your 1 over 1 plus Cp, and then T is also Cp over 1 plus Cp over here. Then this is your noise or disturbance, your reference signal is what we derive the equation from your block diagram over here lah. Alright, but I just want to let you know that if your T increases, alright, it's very nice, but however you're gonna also increase your noise, and therefore the noise is also your limitation, and therefore you, in order to do that, you're gonna reduce your noise by inputting certain noise filter and things like that to make your noise lesser, alright, so that your command response is good. Alright, and therefore these are the things for question 3. Just take a look around. And therefore this thing comes in again, alright. Explain why is it highly undesirable to have low frequency noise in a feedback system. And explain why high frequency measurement noise is relatively unimportant. So if you have a low frequency, your noise is gonna increase. Alright, why do we say so? For the T is your complementary sensitivity function, or your Cp over 1 plus Cp. For some of the case that happens, this T is actually a low pass filter or low pass system, same as for your T over here, because this T deals with your responses and your noise. Alright, so if you have a low frequency, this means that you can allow your T to somewhat maximize. Alright, when you maximize your responses, you are also maximizing your noise, and therefore it is highly undesirable to have a low frequency measurement noise in a feedback system, because a low frequency is going to cause your noise to be amplified, and therefore you want somewhat in between, maybe somewhere over here. At least your noise is fairly can be fairly reduced, so to speak. And I also explain why high frequency measurement noise is relatively unimportant, as also we say that this T itself is a low pass system. If you have very high frequency, you're gonna have zero gain over here, and therefore this whole thing becomes zero, this whole thing becomes zero. You have totally no noise, and therefore the noise is relatively unimportant because there is no noise anymore. But take note that S is a high pass system, so therefore if the low pass system is all zero, your S is maximized, you're gonna have full disturbance. Alright, you got a big disturbance such that your whole system is gonna be a bit cock up and things like that. So therefore we often want our system to have a mixture of the T and the S, such that you operate in the crossover region over here, such that everything is pretty safe. Alright, next question, which is the last question. Given is a feedback control structure with a plant this one and a controller this one. Explain the feedback controller design using the pole assignment. Alright, and what is the characteristic polynomial? Alright, know that until certain points your plant is going to be unstable. Alright, and therefore you want a controller to control your plant. Alright, and we don't use the word controller to control your plant, we use compensator. Alright, so the controller is a C compensator such that it compensates your plant, and therefore let me repeat again, is that the compensator controller compensate the instability of your plant. So your plant is unstable, and therefore you want the compensator controller to compensate of it, to make it stable. Alright, and you have to allocate your poles, and don't just write poles only, you have to write closed loop poles, because closed loop poles are the things that will cause the things to be unstable or unstable. These are the things, this closed loop is very important. So please take note, it's a closed loop poles, it's not open loop. Alright, so you want to allocate your poles to a pre-specified location such that your system is safe. For plant closed loop system, alright, it may be somewhere over here, the poles may be over here. Alright, and it's considered unsafe, unstable, because it's in the right half plane. So the compensator controller, if you were to multiply with your plant, alright, somewhat move these two poles to the other side, maybe somewhere over here. Alright, so you allocate your poles to a specific location such that your system is safe. Alright, you may be also somewhere over here, which location you want, you can input whatever frequency. We have done that in the previous video already, right? In the few previous videos of pole assignment. And so therefore we explain the understandings of why we use the pole assignment. Now what is the characteristic polynomial? Alright, if you remember, S is equals to 1 over 1 plus Cp. T is equals to Cp over 1 plus Cp. We know that your Cp is your controller and your plant. So you just simply sub in your stuff. So it's 1 over 1 plus G over H times B over A. Alright, so this is your controller, this is your plant. Same thing, G over H equals to this. I can rearrange by multiplying AH and AH over here. So I'm rearranging this thing, I multiply by 1. So what I have is AH times 1 is AH, because this is just some revision for you. So AH times this one is AH, and then AH times this whole thing over here, you cancel off with this HA over here. And therefore, what I have is plus GB. Alright? And also for the same thing over here, what you have is H plus GB. So we have closed loop. This thing, all of these things over here is closed loop. S and T are closed loop, if you still remember. And therefore this whole thing, we know that closed loop poles is what we want. Alright, normally when we do things, we want the closed loop poles. As you can see, AH plus GB and AH plus GB is the same. Alright, and therefore this is our polynomial. Alright, instead of AH, I can say that it's A naught H, because the plant is B naught over A naught, so to speak, strictly lah. Alright, so therefore I'll just write A naught H, A naught H plus B naught G. Alright, it's GB, okay, also write as B naught G. It's equals to your ACL, your Diophantine equation. Alright, and so therefore this is the characteristic polynomial, because it's dealing with the polynomial of A and H and B and G. Alright, and this is the answer for this question if you are keen to look at it. Alright, take a second to check it out. Alright, and these are the things that I know for question 1 to 5. And I shall see you soon in the next video.